Particle physics in general is a very abstract field, and every time we talk about the properties of a particular particle, about atoms, or about subatomic particles, only one thought comes to mind. We really want to see a photograph, a real photograph of this object. And today, first of all, we are going to look at some really cool photographs of atoms taken with an electron microscope, and secondly, we'll figure out what's wrong with these photographs. Stay tuned and watch the video until the end because it's going to be very interesting. And of course, we'll start by looking at photographs taken with an electron microscope. Most likely you've come across these kinds of stunning images more than once, but unfortunately these have nothing to do with actual photographs of atoms. Even considering that photographing an atom itself is quite a fantastic idea, and capturing it the way we want is simply impossible. This here is actually just computer modeling. This is just to get ahead of ourselves a bit, so that you don't take these beautiful visualizations as something real. Most often, when you talk about photographing an atom, or flip through popular science magazines, you see results like this. But this result here is already much more interesting. Here, there are some little spheres, but what are these spheres? And why are they arranged like this? Well, first of all, you can see a characteristic orderly arrangement. What does this tell us? It tells us that we are dealing with a crystalline structure. Whether it's a metal in a crystalline state or any other physical body or material, we have an ordered arrangement of atoms. This is precisely the phenomenon that follows that very mathematical logic I talk about so often on the channel. And it is precisely this kind of orderly characteristic arrangement that indicates to us clearly that we have a certain mathematical model that accurately describes the phenomena we are seeking to observe. But in principle, the way things are arranged here right now isn't that important, because what we want to talk about is the photograph of the atom itself. And the photograph of the atom itself, well, these little spheres, these are the atoms. I believe that this transmission electron microscopy is more similar to it. It's interesting and noteworthy to pay attention to these kinds of cutouts. A bit later, I'll show you another, even more detailed photograph. And these cutouts are the result of the electron beam's impact on the material's structure. When I first learned about this, I was really impressed. After all, essentially, we can now cut samples directly in the electron microscope. The sample goes straight into the electron microscope. It wasn't like this before, and the first electron microscopes I saw worked with foils. And just so you understand, foil is this rather tedious and unpleasant material that used to be made with erasers, rubbing it on ultra-fine polishing abrasives. This object was then carefully produced and obtained, and essentially you got something perfectly suitable and appropriate for electrons to pass through, so you could record some scattering or try to illuminate the whole thing. And by the way, I'll just very quickly show you, if you remembered something about transmission electron microscopy, it's also useful to know a few more things. Most likely, you've most often seen photographs of atoms that look like this. And here we see how electron beams diffract on the structure of the sample, returning to that very crystalline structure. And strictly speaking, these are not photographs of an atom in an electron microscope. This object on the right, this scattering, is precisely the scattering of particles on the crystalline structure of the sample being studied. And this is often referred to as an image of an atom in an electron microscope. But it is not an image of an atom in an electron microscope. It is the play of the electron beam on a diffraction grating with its maxima and minima. Next, you have surely seen this remarkable work. This is a work by IBM. At that time, IBM created what was almost the first electron microscope, and with its help, they moved atoms. But how are atoms moved? Individual atoms can be moved either with a specialized mechanical probe or by the application of an electric charge. There are slightly different methods for this. If we delve into them, we'll go crazy and get bored. That's why we won't touch on that. But in any case, these are strontium atoms. Strontium atoms that were moved across a certain field. Again, notice that we see the atom looks like a little ball. A bit later, I'll explain why it always looks like a ball and why it's not some kind of strange structure. If you search for the video Boy and Atom on YouTube, you'll see this kind of magnificence. This is the very work we're discussing, and the guys from IBM made this magnificent image. Move and dance. Also, when you read popular science articles, you probably come across these kinds of magnificent images, and pay attention, this is already a certain zone. Here, nanometers are indicated, unlike the micrometers in the previous photograph. And this structure here is once again a structure formed as a result of the accumulation of a certain number of atoms. Again, it is ordered, again, it is regular. This is all exactly what we've been discussing about materials science. But you've seen things like this many times already, so let's look at something more interesting. And something more interesting would be, for example, to look at a photograph of atoms inside a nanoparticle. Take a look at this specific nanoparticle. It was imaged in dark field. And as you can see, it itself consists of an incredibly vast and complex number of atoms. This boundary here marks the edge of the particle. Perhaps it's some fragment, a bit of powder, a grain of sand, or something else entirely along those lines. And just imagine that every object we see is made up of an even more significantly massive number of objects that we cannot see. And that's very interesting and truly impressive. It's also very fascinating to look at such a magnificent image as this one. Unfortunately, it's very small, so let's zoom in on it now. And here, pay attention, the positions of the atoms are marked on the photograph taken with an electron microscope. But how did scientists figure out that this chaos leads us to such an orderly structure of some apparently even organic substance? I'm not entirely sure. Oh no, it's not organic. In fact, here we have silicon, nitrogen, and vanadium. Judging by what we see, we've recreated the structure from the photograph. Here we have some kind of transition layer, which is very interesting. And this transition layer is made up of atoms of this element. At the very least, it's incredibly cool, because images like these are impressive. This is also the work of an electron microscope. You can see this as well. In the electron microscope itself, you see this, and the simulated image looks like this. Do you recognize those very characteristic arrangements of atoms inside the object? Yes, yes, yes. That's exactly what we're talking about. And there's another interesting point I want to mention here. If you don't know what to look for, it becomes uninteresting. Right now, we've called this video something like fantastic. Images of atoms in an electron microscope, because we understand what we're looking at. But when we see something unclear, some kind of bricks, some holes, some strange objects mixing together, we just get lost. And those who are subscribed to my Telegram channel, and those who aren't, should definitely subscribe, because there's a lot of interesting content coming out there regularly. Know that when the planetary parade happened at the beginning of this year, at the start of spring, I actually posted a note there with photos of what I managed to capture. And if you don't know what you're looking at, to you, it's just an incomprehensible, some kind of starry soup with glowing dots scattered across the black night sky. But when you understand what you need to find, it becomes incredibly... Now this is quite interesting. Here you might think that we as individuals come up with what we want to find, and then we wrap that something in the images we've managed to obtain. But no, that's not actually quite the case at all. In space it works much more obviously because of the gigantic scales, because we have, at the very least, powerful equipment capable of seeing at least a planetary alignment. And when we talk about the structure of atoms, we are always helped by the practical application of the theories we have put forward. And this successful practical implementation of those theories allows us to say that yes, we have obtained the necessary image, and we have visualized it in the correct way. Because the arrangement of atoms, as I previously demonstrated and pointed out in this picture, perfectly aligns with our theoretical expectations, and a practical application has been found, and it works. But let's move on, otherwise it's starting to get boring. So here you can see this kind of thing as well. Again, spheres. There's not much point in dwelling on this, but do pay attention to the arrangement of these atoms. Most likely this is some kind of deposited layer or a specially prepared sample. After all, it's really hard to imagine a situation where particles would spontaneously arrange themselves like this on some surface. Most likely this is still a deposited layer. And here it looks like we're dealing with the structure of graphene, the legendary one. It is indeed that very remarkable element, which is a unique substance. Only a single particle in thickness. This is incredibly interesting because it's something even thinner than ordinary foil, and the properties of this graphene are absolutely phenomenal. We won't dwell on this here, but graphene has an interesting feature. A characteristic arrangement like this. We've mentioned this, we've mentioned that. Now I have an interesting image showing how the probe of an electron microscope works. This is the very probe that we described earlier. Notice, this is a tiny mechanical needle. And when we talk about scanning microscopy, we work with such a device. You can see here it's very well visualized how the probe moves along the surface. Some samples are prepared and record data, and then based on this data, we create the images that we're looking at now. Honestly, I get a little confused. At first glance, I can't immediately tell where it's transmission microscopy and where it's probe electron microscopy. And that's why it's easy to get a bit mixed up. And by the way, since we were talking about probes and tips, and you've already seen how the cartoon about the boy and the atom was made, take a look at this. This is a visualization of how, using that very probe, an atom is moved. There are some misconceptions based on the idea that atoms are bonded to each other extremely tightly and that it's impossible to break these bonds, and if you do, an incredible amount of energy will be released. But usually, people confuse the interatomic interactions between subatomic particles with the interactions between the atoms themselves. Atoms are not bonded to each other that strongly. This is a normal phenomenon. And here, once again, let me zoom in. Notice that atoms are simply being moved across the surface using such a probe. This is also incredibly fascinating, and again, these are spheres. Why are they spheres? You'll find out a bit later. And you've probably come across photos like these as well. This is an outdated type of image from an electron microscope. Why is it outdated? Because as you can see, there's no good detail and no quality processing. Back then, they didn't know how to do that yet. But if you look, for example, at a photo like this, you might wonder, what is this? It's actually very simple. Here we have diffraction scattering in the corner. And here again is the direct atomic structure. And this is most likely a grain boundary. What are metal grains? They are certain characteristic objects where there wasn't enough perfection for the structure to be uniform. So the grains that join together are also made up of atoms. Here we see these atoms, these circles, these spheres. There will also be spheres in the bulk. And here we have a grain boundary, along which atoms are joined together. And all sorts of crazy things usually happen at these grain boundaries. Now you probably remember my videos. Some of the first videos on the channel which were about classical material science, and there we noted that a grain boundary is a defect in the material. And now you probably understand why this is a defect, and why it's the point where the material will start to fracture. You see, here all the atoms are perfectly connected to each other, but here we have defects. This is a common phenomenon, every material scientist knows about it, and now you do too. But this photograph caused quite a stir, and it's notable because, first of all, it won at some prestigious scientific photo exhibition, and it was taken with a DSLR camera. Honestly, I don't remember the author's name, but I'll mention it in the comments. But the most interesting thing is this right here. Right in the center, the object you see is an atom which was photographed using a DSLR camera. It was trapped in a special device, and in this trap it was suspended in mid-air. Because it was suspended in the air, that's basically how this result was achieved. It's somehow possible to describe, characterize, and observe it. And again, you see, here is this sphere, here is this little ball in the center of our image, and here is that atom that was photographed. Unfortunately, I also don't remember right now exactly which atom this is, but again, it's a sphere, and again, it's an interesting object to study. And very often, people also say that in YYY, scientists managed to capture a photograph of the bond between atoms, and that will also come up. Essentially, it's a photograph of an atom. A bit later, we'll find out that the word photograph isn't entirely accurate, but for now, we use it because it's simply convenient to say so. And here it seems we've managed to capture the bond between these atoms. Take another look at the spherical-shaped objects. And this very thin, narrow line here is what serves to represent the bond between these spherical particles. And what is located at the point of the bond? Essentially, in terms of the parameters and paradigms of the world, we can't really describe it precisely. Let's put it this way, it's not entirely accurate, but those who watch my channel and are interested in the topic already know what I'm talking about. Basically, these little lines between the atoms represent magnetic interaction. It's actually a bit different. There are slightly different forces at play, but this is the simplest way to describe it. And this is how a microscope sees magnetic and electromagnetic interactions. Oh, right. And I really should have started with the simplest thing. I should have started by showing you what an atom looks like according to Rutherford's model. Now, the modern model of the atom assumes that these particles labeled as electrons are no longer in exact positions, but rather in a probability cloud. I think, once again, you've seen this picture in my articles on the channel, so we won't spend much time looking for it now. But the point is simple. But why do we always see spheres? Why do we always see a ball? That is because whenever we engage in a direct interaction with a material that has an organized atomic structure, whether by employing a focused electron beam or a specialized probe scanning meticulously across this structure, we will always observe and detect this outer electron shell. And essentially a photograph of an atom or an image of an atom. This image is in fact the electron shell itself. Where does the sphere come from? Here is the sphere. I hope that the movement of the mouse pointer is being recorded along with what I'm saying right now. And yes, here is the circle, here is the sphere. So what exactly do we see in photographs of atoms? In those very fantastic photographs that are featured first in our video today? We don't see the nucleus of the atom or anything like that, but rather this like a shadow that has formed. We'll talk a bit more about this in a moment. But the methods we've just looked at and the objects we've studied are not the most advanced ways of studying. For example, there is something called psychometry. This is a complex technique which we won't spend time on right now. But let's take a look at the photograph. After all, not so long ago this was featured in all the popular science articles and it also appeared on my channel. This is that magnificent photograph taken in one of the laboratories. What do we see here? Well, first of all, we see that there is no clear boundary. Why? Because of thermal motion. We have captured the thermal motion of the atom. Here it is. And these spheres here are once again atoms. Essentially, the photograph differs from everything else we've seen only in its level of detail, its resolution, and in the presence of the background thermal motion. Yes, we have once again confirmed that our idea about the constant thermal motion of atoms is indeed correct. And here is your proof. This halo around the image, this blurred area, is where the atom jumps around. But at the same time, we've confirmed that the atom does not have a specific position. To some extent, this overlaps with Heisenberg's uncertainty principle. But essentially, there is nothing new in this image. Well, my friends, now it's time to answer the most important question. What's wrong with the photographs of atoms? What's wrong with what we've just seen? And this question is truly fundamental. It's very important because simply looking at the fantastic photographs taken by scientists isn't as significant as what we're about to discuss. There's another interesting point. You've probably noticed that regardless of the research we conduct, or let's say the technological era we're using, we always see the atom. In the photograph, it always appears to be shaped like this donut, or like this sphere. Why does it turn out this way? And can we expect a different kind of image? Can we expect greater detail? No, we can't when we use this kind of thing. And you probably remember the photograph of the hydrogen atom that circulated on the internet for a long time and stuck in many people's minds. That blue background, that center. I'll show it now during the video editing because I didn't include it in the selection. I forgot about it. Now, you might be thinking, well, that is where the true essence of it really lies, but actually, no, it is not quite like that at all, and that does not truly represent the detail. These images were carefully constructed from the raw scientific data we had available, which came from that very same celestial sphere. Essentially, it's a mathematical model that was given a detailed visual representation. It's not even direct research. It's not exactly a photograph. It is a precise piece of modeling. Keep this in mind when you read those flashy headlines like, "Oh, scientists photographed an atom." As of today, there is no technology available today that allows us to directly photograph a single atom. It's important to remember this. And so the so-called photographs of atoms are actually not photographs of atoms. And why is that? It all comes down to the specifics of how these photographs are made. Let's start with the simplest thing. What, in your opinion, is a photograph? I think every single one of you would say that it's the result of light interacting with some kind of light-sensitive recording layer. On this sensitive layer, whether it's traditional film or a digital sensor, a clear image is formed of the object we see with our own eyes. And based on this, we can quite reasonably assume that the object we see with our eyes has been successfully captured and recorded. In this photograph, the mechanism will be roughly the same. As a matter of fact, that is really how it works. And actually, the mechanism of a simple optical camera and our own eyes is remarkably similar. And the essence of perception, at its fundamental level, is also very much the same. But when it comes to photographing particles, when it comes to what we call photographs of atoms, things get a bit more complicated. And it all starts with the simplest thing. There is such a thing as the diffraction limit AB. This means that when we work with specific and particular objects within a certain size range, and that size range becomes extremely and unacceptably small, we can no longer capture direct photographic images of these objects. This is because the light we use to create a photograph, the light that is visible to the human eye, this range of electromagnetic radiation has certain parameters and, as we remember, is essentially an electromagnetic wave. We can assume that if an object is significantly smaller than the wavelength of light, then we will not be able to see anything at all. We will see the result of diffraction. And that's pretty much how it works. If we reach this diffraction limit AB, it turns out that visible light hitting the object does not reflect off of it, but instead starts to bend around the object or diffract on it. This means that a particle whose physical dimensions are comparable to that of an individual atom is fundamentally unable to be seen optically. Light will not be able to interact with this object. Light will not be able to reflect off this object. And of course, we won't be able to capture such a photograph. But despite all this, we've noticed that there are photographs that, as a matter of fact, we've just looked at. Any image produced by an electron microscope is usually obtained through the interaction of an electron beam with the object we are studying. Of course, it would be worth mentioning the different types of electron microscopy, transmission, reflection, and many others. But the most important thing here is just one point. We replace ordinary visible light with a beam of electrons. And the electron beam can interact with objects and already has different wave-like characteristics compared to visible light. This allows the beam to be reflected, or to bypass the objects we see and transmit through the sample completely. In all cases, no matter which one you take, it's all very simple. We interact with a certain object and get something like its shadow. You can call this differently and describe it in various ways. But in all these cases, we are dealing with an entity that resembles the object's shadow more than the object itself. In general, you could say the same about optical microscopy and focus on the fact that light is also somehow reflected. And in reality, we don't fully understand what our eyes actually see. But still, this is something you can dig into endlessly, and the discussions can go on forever. There is never a true limit to how deep you can go into knowledge. However, I believe it's sufficient to use the limit that follows from the very nature of human vision. And in some ways, the optical microscope replicates this nature. The electron microscope works differently. We do not see the direct interaction of visible light with these objects. But what we do see is, for example, how the electron probe in scanning electron microscopy moves across the sample's structure and captures its topology. And this way of framing the question turns the atom into a kind of bag, with something inside. This bag has neither a surface nor a shape, and to some extent, one could say that the atom as such does not exist. That would be technically correct, but it wouldn't have any practical impact. Based on theoretical knowledge, one can confidently state that the atom, in the form we want to see it, simply does not exist in that way. The atom is a somewhat different kind of particle, an atom. It is a more complex particle, and the many videos on the channel that I have already made on this topic confirm exactly that. I don't want to repeat myself, so if you have any questions, please find all the links in the description. You end up with something like a photograph. What does that mean? It means that not a single photograph of an atom is taken directly. It is always some kind of indirect investigation, and an indirect investigation is the reconstruction of an image based on the digital data we have obtained. And by and large, with photographs of atoms, there is only one thing that's different. It's not a photograph of atoms. It's a kind of illusory imagined model that is created using computer modeling as a result of processing the data we collected from the sample. We take the model that seems correct to us. We carefully apply to this model a certain set of knowledge that we have, and we overlay the experimental results we've obtained. Then we combine all of this into a comprehensive final model. As a result, we get, let's say, a detailed and structured table of information that we can imagine as an image, and we do this successfully. And here, this intersects with virtually all methods of studying subatomic particles and atoms themselves. The question arises, which search method then would be the correct one? There is no correct search method. We have a set of these indirect measurements which we use as a way to search for physical objects. Well, now that we've discussed all this, I hope you formed an understanding of what's wrong with these photographs and why they're not exactly photographs of an atom. The fact is, the atom is a useful model, a well-developed, well-functioning model, but it does not reflect the true structure of the atom. No, this does not mean that the atomic model is incorrect. The atomic model is correct. The atomic model is suitable for all its practical applications and for describing the properties we need in practice. However, the atomic model may turn out to be incomplete. In much the same way, the atom itself was once studied. If you trace the history of atomic physics, you'll find that it started with the plum pudding model, where it was assumed that inside the atom there were some negative charges, which were later called electrons. Then came Rutherford's model, which was a significant advancement over those earlier models. Now we have the Schrödinger model, which it builds upon Rutherford's model and states that electrons in the atom are not like planets orbiting around the nucleus of the atom, but instead have only a probabilistic location there. And here, knowledge from quantum physics and much more has been incorporated. This is a completely normal and appropriate process. Therefore, to say that all of this is wrong is also incorrect. At the same time, we try to photograph this atom, we try to latch onto something and obtain some real experiment that we can observe with our own eyes. But the problem is, we can't do this because everything we've just listed directly affects the atom's ability to interact with direct research methods. Well, I hope you found this interesting, and I hope you learned a lot of useful and new things from this video. So, for now, I'll say goodbye to you. Thank you for watching until the end. Be sure to subscribe to the channel and like the video if you haven't already. Take a look, the link is in the description, and just recently I finally published a book. I finally found the time to finish this work, and please, the link is also in the description. I called it Modeling the Universe. And I believe that the various entities we frequently discuss on the channel are, let's say, actually presented there in the form of a brief, clear, and engaging description. I think it will be very interesting as well, so please follow the link in the description, check it out, and take a look. And basically, that's all for now. Thank you very much for your attention, all the best to you, and see you next time.